So, hi everyone again. We will resume now the morning session with five talks. Each talk will be 20 minutes. First of all, I would like to thank the organizers for amazing conference, very interesting, very challenging. Thank you very much. And the first talk will give Iurii Marko. The title of his talk is Spaces of Idempotent Measures of Countable Support. Iurii is from University of Lviv.
Thank you so much. Thank you so much.
Yes, please start.
Should I start? Yes. Good morning, everyone. First of all, I'd like to thank the organizers for the invitation. Today, I will speak on spaces of idempotent measures with countable support. Briefly speaking, idempotent mathematics is obtained when we replace traditional traditional arithmetic operation by an idempotent one, like maximum. Actually, the original definitions of idempotent mathematics deals with coefficient from -infinity to 0. Here we change the variable by means of the exponential map e to t. These changes allow us to have the same set of coefficients for different types of measures. Therefore, we use the unit interval and additional instead of multiplication. To be more formal, we first consider the case of compact Hausdorff spaces. It is well known by the Rees theorem that the probability measure are naturally identified with the functionals of the 1x space on X of continuous functionals which are linear, positive, and normative. Similarly, one defines the set of idempotent measures on space X as a set of functional satisfying the condition. They preserve constants. The next, they are homogeneous with respect to multiplication. And the last condition, they preserve the maximum. In the talk, idempotent measures are identified with density function of subset of x times 0, 1 with following properties: saturation, consisting the bottom, and reaching maximum. Without requiring of X to be a compact space, we define an idempotent measure as a set of all subsets of X times 0 and 1, and denoted it by I of X with following properties. Every set is closed, saturated, consists X times 0, and also point 0 x1 for some x. About metric, we end of the set I bar of x with Hausdorff metric, which induced by Max metric on X times 0, 1. For a given set A, we define as the support of A by a formula. This allows us to consider to construct new subspaces of I bar of X. There is some of them I bar beta of X with compact support. Also I bar omega of X with finite support, and I bar A of X with support which are the most countable set. And the last one, as is written on the slide. Also, we need the notion of absolute extensor. A topological space is an absolute extensor, shortly AE, for matrix space, if for any matrix space X, any closed subspace A of X and continuous map F A from Y, there is a continuous map G from X to Y such that G restriction onto A is equal to F. The following examples are Rn, any Banach space, any convex sets in Banach space. So, recall that the space X is an absolute retract in the class of all matricial space. If X is a retract of matricial space Y in which X is closed subset. It is well known that AR that the notion coincide. For investigating absolute retracts and absolute extensor, Charles Horvath defines the notion of C structure for these spaces. Let us define some of notion from that paper. The notion of C structure, also the notion of an F set, and the notion of LC space. Please see all this definition on the slide. So Charles Horvath showed that a subspace of with a C structure is an absolute retract. So we define a C structure on the space of an idempotent measures, and our main results are the following proposition, which states that some non-compact of idempotent measures are absolute retracts. As we work with the Hausdorff metric, we only speak about Borel types for closed sets. Here are shown some of them on the slide. We introduce the following space K of X by the hyperspace of all non-empty compact subsets of X. Also by A prime, we denote the derived set of all accumulation points of A. In paper, hyperspace of countable compacta were considered countable compacta AN of X and A omega of X. They are defined with the following formulas. In some sense, these spaces are analogs for idempotent measures of the spaces introduced by Banach and Quarters. and the results of the results on absolute extensions and Borel types allow us to use methods of infinity dimension topology in investigated space of idempotent measures. That's all. Thank you for your attention.
Thank you very much, Iurii.